How's it going, everyone? Javier Gonzalez again. Now, looking at the NeetCode problem solution as a way to identify all of these particular patterns that come up when it comes to solve real life problems using tools like data structure and algorithm, specifically with EX6 or the JavaScript. So, by looking at this, and as a way to improve also my problem solving skills using now JavaScript, but being able to use now, so by using this data structure and algorithm, this way of how you can now store data and apply some operations up to this data, as well as the series of steps or the common series of steps to solve common real life problems. So, for example, like searching, sorting, something we're gonna see that later. Uh, in today's video, we're gonna take a look now at this particular exercise of two pointers, because so far we have looked at the arrays and hashing, uh, and the methodology of this is set a 45 minutes where the first 10 minutes we're going to describe is what we have done and reflect about all the things that we have learned so far. Then 20 minutes to see and understand what is the problems and how we can come up with a solution. If we couldn't find any solution, any problems, then take a look now at the uh, video solution. So, because first we'll look at the array hashing, this entry point as a way to how you can now solve these common problems, specifically by using data structure like arrays and hash. Okay, and how you can now with this first problem, how you can count is duplicate, how you can check if there are duplicates in a particular collection. All right, in using the EX6, we can use this a particular data structure called set to solve these particular problems. Okay, but if you don't have that, if you need to implement that, well, the idea here is to, as we iterate through all of these elements, we're gonna count them using a hash map. When we're gonna uh, add those numbers that we don't have them here, okay, and as we move on to the collections, if we already have that number in our hash, it means that it's a duplicate, therefore it is false. So the idea here is by being able to describe this in plain English, then how you can implement that solution. But as as you solve more complex problems, the idea here is that you are going to develop is now a mechanism of how you're going to provide all of this series of step-by-step solution. And there is a reason why I actually slow down word by word, because this, it might sound boring, but the thing that it allows you to do, or that it that it can it provide you, is things like this. So, for example, now you are capable to see me here streaming this video and me learning about this array and hashing, but it's because the way how that data is transmitted is following is a particular protocol. Perhaps in this case, they're using to send data over the cable. I don't know if they're using perhaps is WebSocket or HTTP, all right, but or sending that as an array of chunk of data. The whole point of this is to see how now all of these particular problems come out and how you can solve that. By most of the time is to split them, and then like hashing or taking bit by bits of each one of those problems that you can compose that to solve more and more ambitious goals. So for example, streaming data like this. Right now, this is not a real life streaming data, uh, but for example, if you use Twitch, that's something that you can go with. In this case, we are just only recording this. So the GPU is actually processing all of this image here and then store that on disk. So there is a streaming process locally. And when I upload that to a YouTube platform, which is something that you're gonna see, you're gonna now see an upstream or streaming, not in your local computer, but across different computers, which things becomes now beautiful and interesting. So, but in any case, we got to look at the contain duplicates, then valid anagrams as a way to see how by now interacting and work with strings and converting into an array, apply some transformations to this collection of values. So for example, hey, I want you to sort these elements. And once we have these elements sorted, this array sorted, then transform each one of them into a string. And then I want to compare both strings by applying that particular process. Sorted, this is one way to solve this. Sorted, so transform them into an array. Sorted, and then give it back as a string. And then we're going to compare that. So the two sum is as a way of how we can now start to work with representations, which is which is that count the number of, or give me the index of those numbers. Give me the index of those numbers in an array that match, that when add up, match to a target. So the idea here is that by iterating through all of these elements, as we do that, we're going to now store that. But the way how we're going to store that is by storing is the key as the value and the value as the index. All right. So by now looking at the difference between that element in that position and then the minus the target, and see if we already have that number inside of our array or inside of our hash, by actually using is the absolute value of that. If we already have that, okay, now we can provide is the index. If we're not, well, there is none. So this is a way of how we can start to see the representations of objects, or how can we use this data structure to represent something. And software engineers live in this abstraction hell, or in this representation things, as a way to allegedly improve things, but at the end of the day we just end up providing much more complexity than is required. But in any case, because most of the time we need is to learn the mathematics, learn cryptography, because those formulas and techniques are helpful when it comes to determine is what is the best way to solve a particular problem. But in any case, so the other is group anagram. Is see as how you can now work is with your hash, with key, and the value is the an list, a collection of values in there. The top came frequent elements and the string the code was a great example of how you can now represent data. And here is how you can use now a particular data structure, giving a collection of values. How you can use now is this exactly how you can use now this collection of values and find out what is the most frequent element for that. And it's similar to the string encode. This one, is a very interesting way to solve that, because you have now all of these collections of values, numbers, and then you want is to count the number of occurrence, and then after that, you want is to represent you want to represent is the number of occurrence using a data structure like an array where you have index, where each one of those index represent is the number of time or the occurrence that those value actually are. And as you're going to do that, their value will contain is the most key frequent values. You can have them into an array or into an set, right? As a way to store is unique values. But the whole point of this is that once you create that array that will represent is the number of occurrence, their index we're going to represent is the number of occurrence, we are applying is simple arithmetic and representations. And then if you want to know, once you populate that collection of values, okay, because this array starts from 0 to n, okay, and the length of that new representation will be is the same as our collection. Now we can is to say, all right, it'll make much more sense to reverse that and give me now the k most frequent elements from that. So this is something very, very powerful, similar to the string and the code, where he would say, how can we now add piece of data here when it comes to encode a data or in strings of data, and when we want to decode that by reading is the data that we insert in that string, how are we going to using index, how are we going to move as a way to identify as a way to extract that data. Is that, hey, this piece of data is indicating is the length. The separator indicate that this is when the string actually start with, and the until it ends, so we can actually extract that and actually is the code that giving a particular string. These two examples are actually quite interesting, helpful when it comes to encrypt some data, or for example here when you want to know is the most frequent elements. This is now another quite interesting element, like or algorithm like product, the product of array except self, as a way to walk through all of these elements and calculate is the prefix followed by the postfix, and similar to the value Sudoku, as a way to now work with this representation. So how you can actually is make this thing work by looking at the column and by looking at the by looking at the column and the rows, in each one of those 3x3 cells actually going to represent is a position in the matrix. So this is so the values was a very interesting exercise, because this is how you can, for example, create applications like the tic-tac-toe, for example, which is something that I'm going to build. I definitely need to do that completely. Yeah, I definitely need to do that. I definitely need to do that. Oh yeah, I did. And then finally, we look now at the valid palindrome, which is like, hey, how you can now identify if this word is a valid palindrome. So by taking that, which is actually, this is my solution, and a palindrome is when a phrase without the characters when you're removing all the non-alphanumeric characters, and it reads the same forward and backwards. Okay, so the idea of this is how you can start to working is with this string, this collection of values, but now using is this new paradigm, or not that new because it's nothing new. To the language is new, but in other language like Python and Ruby, they actually implemented the iterator protocol, which is a behavioral design pattern as a way to, I don't care what is the underlying data structure, how the underlying data structure is implemented. I just only care to get the data from the next, to get to get the data at that position, and when I call you again, the next element, and that's it. That's all, right? Uh, this is something useful, for example, in graph, okay? Uh, graph trees as a way to use this particular function or this particular pattern to iterate through this collection of value, which to me is quite interesting. Yep, it is. It is. And the point of this is that as we iterate through this collection of values, okay, uh, let's go to now transform each one of those elements to lowercase, and we're going to compare using the match function, which to me is quite beautiful. If you don't have that function, you need to create now a uh, a representation from the A to C, and then the 0 to 9. Okay, you create a table, and then you're going to compare if each one of those strings actually are the same as you have in your hash. But we don't, because we don't need that. Luckily for us, we have this match, which is a nice convenient function in JavaScript that it evaluates the regular expression. And here's when we're telling that. So if that actually match uh, an alphanumeric number, okay, all right, good. Now let me actually add this to my string. But the pattern here is that this is pretty much like playing with Lego blocks, you know. All of this, what we're doing is just playing with Lego blocks in a very abstract way, but that's what we're doing. There is no sound here like, but this is a way of how you can think of this, right? As a way to get yourself the feelings, the sensation that you're actually doing that. And once we actually create our palindrome, okay, we want to know if that particular phrase or that particular string, once we transform to an array and we reverse that and we get the string, we want to see if if that palindrome reverse is the same as the palindrome that we build. All right, if it is, good. So far so good, because there is nothing extraordinary here. You know, there's actually nothing extraordinary here. Again, this was very straightforward with in JavaScript, in modern JavaScript. Sorry, my bad. Now it is time to look at another example here, which is with 2 pointers. Now like this, to sum 2 input array is sorted. Let's get into this. No, but not here. In here. Okay. Let's get into this. To sum 2 input array is sorted. Okay. Arrays to pointers and binary search. Okay, and they already tell you what to do. Okay. Okay. Interesting that they already tell you. Okay. Giving an index array of integers number. Giving a one index array of integer numbers that is already sorted in non-decreasing order. Why do you like to confuse them? In a non-decreasing order, which means in an ascending order, sorted in a non-decreasing order. In a non-decreasing order, which means it's an ascending order. Oh my fucking god. Find two numbers such that they add up as okay. Find two numbers such that they add up to a specific target number. But this is a two sum 2. Input array is sorted. Interesting. Let these two numbers be number index 1 and number index 2, where 1 is less than the index 1. Okay, this is the range, where index 1 is less than the index 2 and less than the length of that. Okay, so this index, okay, it means that given this one index array of integer numbers that is already sorted in an ascending order, find two numbers. Exactly, as you can see, they are already sorted in an ascending order, in a non-decreasing order. 2, 3, 4, minus 0. Okay, it includes that. Okay. Find two numbers such that they add up to a specific target number. Okay, find two numbers find two numbers such that they add up to a specific target number. But this is now is find two numbers here. Okay, find two numbers such that they add up to a specific such that they add up to a specific target number. Let these two numbers be numbers index and numbers index. Where 1 is less than index 1. Okay, where the first index, okay, when you're going to find is the first index, okay, which means that the first index that you're gonna find, okay, which means that the first index, let these two numbers be numbers index 1 and numbers index 2, where the index 1 is less than the index 2, which means that is before the index 2, and that index 2 is before or at the last position. So here now is describing is where you can find this number. Okay, return the indexes of the two numbers, index and index 2, and index of 1 and index of 2, added by as an integer array index 1 and index 2 of length 2, and added by 1. Return the index of the two number index 1 and index 2 added by 1 as an integer array like this of length 2 as a tuple. What is an array? Here, the texts are generated such that they are inexactly, okay, the tests are generated so that there is exactly one solution, which is great for us. You might not use the same element twice. Your solution must use only context constant extra space. Okay. So now it adding is a new layer of complexity here. Is that your solution must use only constant extra space. Okay. 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 So now it's saying we must not use any data here. Okay. Um, exactly. So hash is something that we shouldn't use this. Mm-hmm. And the other is this. So because our array is already sorted and we have all of this condition, so for this particular case, as we iterate through this element, we check their value, which is 2. Okay. We check their value, which is 2. Mm-hmm. And if we, okay, we check their value, which is 2. And now the target can be, okay, now the target can be is negative and positive numbers. Okay. And the numbers will be negative and positive. Okay. And the constraint is that at least we will have is 2 elements in the array until 1,000. Think 1,000. No, yeah, think 1,000 of elements. Okay. Numbers is sorted in non-decreasing order. Okay. The tests are generated such that they are. The tests are generated such that there is exactly one solution. Okay, so given all of these specific constraints, okay, all right, okay, giving all of these specific constraints about this. So, if we already have this collection already sorted, and we are guaranteed that let these two numbers index 1 and numbers index 2, and we are now have this guarantee that we're gonna find is the first. So the first element that we find will contain is the index, and then after that we're gonna find is the first element that match when we add this to the target is the index is less than the second index of the another element. So one way we can do this is by doing is this. So if we find, for example, because after all we're going to guarantee is that it only exists one number, okay? So there is exactly one solution for that. So if we say, for example, this 2, and when we subtract that to the target as a way to get now the proper value, okay? And we can hold that value, and we're trying to find that value across the and we try to find that value across the other array. If we find it, great. If we don't, what is the output here? It seems that we are always gonna get that. Okay. So one possible solution is this. So because we already have this collection of elements already sorted, and we are guaranteed that we can find this first. So the first element that we find, it is index is less than the second element, all right, in that collection, and they of course are bound to the length of the array. Uh, mhm. Okay. So one naive approach that we can say is that we're going to store the, because we only want to use constant extra space. So store the computation from, or store the difference of the first element minus the target. Okay, we're gonna store that. Okay, and then we wanna try and exactly store the difference. So first is to iterate through the array, right? So the idea is to store the difference of the first elements minus the target, and iterate, store the difference of the first element minus the target, call it complement, all right, or call it as difference, or Jesus, store the difference of the first elements minus target, called difference, okay, and then we're going to iterate through. Okay, so store the difference here. Store the difference of the first element minus the target. Okay, we're also going to store is the we're also going to store is the difference yeah, we're also going to store is the index. Okay, store the index of the first position. Store the index of the first position. So we are assuming now that the first elements, since here they are telling us that that index is less, is in a lower position than the next index. So we can assume that the first element here is the one who we wants to know about this, right? We are making this assumption here. So store the index of the first position, okay, then iterate through the array, finding the iterate through the array, finding the value or the difference, and return the index. And last but not least, we're going to actually return is the we're going to return is we're going to return is the index, exactly. So we're gonna return the index, the indexes added by 1, right? Like so. So far so good. It seems to be pretty straightforward. So here we're gonna store is this, and say the difference, like so. This is difference. Where here we're gonna say is numbers, get me the first element at that position. All right. Numbers minus the target. Okay. I want to store is the number one index. Okay. So number one index, which is the of course assuming that, which is 0, because we're starting from that position, and then we're going to iterate through that collection by saying numbers, and since this is already sorted, we can just iterate for each one of those elements. All right. Or we can use do, instead of for each, because after all it's going to mutate the array, we can use this map as a way to return is a new state, or we can use is the for of syntax, which is now a convenient syntax that allow us to iterate to iterables, those who implement the iterable protocol, and extract the values here when you say, hey, this will be the number, the num of iterables. All right, and here you're going to now evaluate this by saying is counts number. I want to see now if the difference is triple equal. Okay, it's triple equal. I actually thought about that, because by using this object.is, you can make sure that it's truly the value, because unlike triple equals, it doesn't check, for example, it's not a number. We are here guaranteed that we are receiving is this as a number. So far so good. But in this case, because we're not getting that, because we just want to guarantee that those two values are the same. So the difference, so if the difference is the same as the number, okay, so if the difference is the same that num minus the target, okay, at that moment, well, in this case it'll be something like, so this is the difference, which is what we need to find. Okay, and when you add up, exactly. So is the difference, which is this number here, exactly, is the difference, all right, actually is that number, because is that is object.is, is the difference same as the number, okay. So for example, in this case, that's why here we need to put is like, here we're not counting is, yeah, is the difference, assuming that the target is greater than that value, we're gonna get in a positive number, okay. So is the difference the same as the number? Then we're gonna say, okay, let me now store is the number 2 index, which is initially 0. Let me now store that index, number 1 index. One of the great things of this is that we can access to the num followed by the index, okay, which is key. I know it when you iterate through this number here, for example, yeah, when we iterate through this number using, for example, the for cons, I think it's key and value of this, to console log the, oh no, you need to transform this into entries. My bad. You need to transform this into entries. So now it followed the iterator protocol that you can consume here. But now this will be is the key value, which is the index and the number. So the number 2 index, it is now that index, and I want you to break it. Yep, break. And here, after that, I want you to return is the number 1 index plus 1, followed by the number 2 index plus 1. One of the trade-off with this is that we are always assuming that the first element will be always 0. Will be that. We're going to start from there. You know, wrong answer. What is the target? Oh, the target is 0. Oh, okay, that's quite interesting. And interesting. So in this case, math that abs to get the absolute value from that. Output 1 and 1 and expected 2. Interesting. Okay. Oh, it's because we will need to start to count. No, I get it. We will need to start to count from. We will need to count to start is from that. So ignore is the first element. If index is equal to 0, continue. Because we will need to iterate is from the second element. Exactly. It's because. Okay. Okay. I get it. I get it. No, it's okay. It's okay. Um. Okay. Exactly. It's because here we are assuming that this is from 0. You know. Here we are assuming from 0, so it means that we can use. So there is no constraint about the. Yeah, there is no constraint about how can we iterate through all of these elements here. Okay. So there is no constraint about how exactly. There is no constraint about how can we iterate through all of these elements here, which means that the space complexity is something that we don't care. The time complexity, we care about the extra time. This we care about. Okay, your solution must use only constant extra space. Exactly. We care about the space, but we don't care about the time. So because of that, we can now iterate through these collections. Okay. That's quite interesting. That's very, very interesting. So because of that, we can iterate through these elements. Okay. Okay. There is no constraint about time. And the problem with this approach is that because we are assuming that we always going to have is the first index. So we will need to somehow update that index. You know what I mean? That's what happened. We need to somehow find a way to update that index. So because this is now the way of how you can find index here, okay, and you might is starting to use some interesting. So since this is already sorted, okay, we can use, since this is already sorted, we can use this the binary search as a way to find them. And the binary search is that you're going to find that number and split and split and split and split and split and split. Yeah, I think this is something that we can use is that. Split.
Let's solve LeetCode 167 to sum 2. So we're given an input array that's already sorted in ascending order, and we want to find two numbers that sum up to some target that we're also given. So in this case, the target is 9. The two numbers that sum up to 9 in this array are 2 and 7. And we want to return the indices of these two values, but the catch here is that the indexes are 1 based. They're not 0 based, so the first element has index 1, the second element has index 2. I don't know why exactly they did that in this problem. It's kind of weird, but they did for some reason. We're also guaranteeing
you return an array both index 1 and 0 are not 0 based. In this case, giving a one index array of integer. Giving a one index array of integers. A one index array of integer. Okay. So they actually is indexed is per 0. Okay, what in the F? They already indexed that is per. So if I do this, numbers dot 0 because you must return something. What's going to return is 1 0. Chill. but in that position you already got that. It's just a way to confuse it, because after all, this example works for one particular use case.
Guaranteed that there's exactly one solution and we can't use the same number twice. So in this example that they gave us, the two first numbers sum up to the target. So that's not really a good example. So I'm going to look at my example over here that I drew. So the first idea that might come to your mind is just look at every single combination of two numbers. So let's say we're starting at the first number 1. Let's look at every number combined with 1 and see if it can sum up to the target 9. So first we check 1 plus 3. That is 4, so it's not 9. Then we check 1 plus 4. That's 5. Then we check 1 plus 5. That's 6. 1 plus 7 is 8. And 1 plus 10 is 11. So now we've gotten to the point where at 1 plus 10. But the interesting thing about this is the first combination that's greater than our target 9. So do we have to keep looking at the next element? Since we know the array is already sorted, there's no number that's going to come after 10 that's going to be added to 1 that could possibly sum to the target 9. So since 1 plus 10 is already greater than the target, we don't have to look at the remainder of the array because there's no number that could possibly come after 10 added to 1 that would ever be the target. Every number is going to be greater than the target, so we don't have to consider 11 anymore. So we basically remove it from consideration from our array. So we didn't find the two numbers that sum to the target. So now let's try if there's any combination with 3 that could possibly sum to 9. So we start at 4. So 3 plus 4 is 7. 3 plus 5 is 8. 3 plus 7 is 10. So this is the first combination. 3 plus 7, which is 10, is greater than the target 9. So we don't have to look at any number that comes after 7 because we know that it will never equal the target. So we can basically say, well, 10 is removed from consideration. We don't even have to look at it. So we couldn't find a combination with 3 that could sum to the target 9. So now let's check the next number, 4. The first number after 4 is 5. In this case, 4 plus 5 is exactly our target 9. So we found the solution. Of course, since we found the solution, we don't have to consider any element that comes after it. So in this case, 7 is removed from consideration and we can return our solution. And remember that these indices are based on 1. So the first index is 1, the second index is 2, 3, and 4. So the indices that we're going to be returning are 3 and 4. So since this is a brute force solution, we're having to iterate through the entire array, which is length n. And we're going to potentially do that in the worst case n times for each number in the array. So then that means our worst case time complexity is big O of n squared. So it's not very efficient. But can we use the fact that this array is sorted to our advantage? Let's look at the picture we just drew. First, we eliminated 11 from consideration in the array. Then we eliminated 10. Then we eliminated 7. So we're basically eliminating elements from the end of the array in reverse order. Can we use this to our advantage? This is basically the intuition. Remember, this array is sorted. We can use that to our advantage. So let's try the exact same problem with a slightly different algorithm using what we just learned. Our target is still 9. Since we're eliminating elements from the end of the array, we can use 2 pointers. One pointer is going to be at the beginning, or a left pointer. One pointer is going to be at the end, or the right pointer. So we currently have a 1 and an 11. Let's add these together. 1 plus 11 is equal to 12. So that's greater than our target of 9, remember? So since this target is too big, we need to decrease it. We have a choice of which pointer to shift. If we shift our left pointer here to 3, we're going to be increasing the sum. We don't want to do that since the sum is already too big. So instead, let's take our right pointer and shift it to the left. Now we've decreased the total sum, so let's recompute it. 1 plus 7. Now it's 8. This is too small. We decreased our sum too much, so now we need to increase it. So since the array is sorted, we can take our left pointer and shift it to the right to increase our total sum. Now we've increased our sum, so it's now 3 plus 7. But we went too far again. Right now it's too big again. It's bigger than 9. So what do we have to do this time? Well, we want to decrease our sum, so we're going to take the right pointer and shift it left. So now we decreased our sum. Let's recompute it. 3 plus 5, but that's 8. So again, we got to 8. It's too small again, but we're guaranteed a solution, so we're going to keep looking. Since our sum is too small, we're going to increase it by taking our left pointer and shifting it right. Now we can't really shift our pointers anymore, so we better be at the right solution. Let's check. 4 plus 5, that's exactly 9, so we got our target. And so we want to return the indices of these, which are going to be 3 and 4, right? In this case, we don't have to iterate through the entire array more than once, and these left and right pointers are never going to cross each other. We don't need extra memory either, so our time complexity in the worst case is big O of n. We found a linear algorithm using 2 pointers to solve this problem. We didn't even need extra memory. Now we're ready to code up the...
Oh, yeah. Okay. Alright. This is quite interesting. So by using the 2 pointers here, and keep track of the pointer, and then update that, and keep track of the pointing and update that. Check updated, 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 check updated. We were now able to do that in linear time. Oh my God, my brain hurts. My brain hurt. Oh my God. Oh, for French toast. Yeah, because my solution was to assume that the first element is fixed, but of course that's naive. That's not what you need to. You know, it's like that's not. That's not. Basically, it's like no. It's not smart. So that's why we do that, and that'll be all for this video. Jesus, take care. Bye bye.